All right, students. So we've been working with integration here, and there's a concept that's really key to calculus. It's called the fundamental theorem of calculus, and it connects the idea of an integral to the idea of a derivative. And we've sort of taken this for granted that we can do antiderivatives and that it tells us the same thing as an integral. But that's a really not intuitive thought. Like, why would it be that the derivative, which is talking about the slope at a point, the rate of change, why would that concept be related to the integral, which is talking about the area that is underneath the curve right there? And like, how are those two ideas related? So, what I want to show you is one idea about the fundamental theorem of calculus that helps to relate these two ideas. So, here is claim number one. I claim that your function is equal to, this is true for any function that is differentiable, that it's equal to the derivative of 0 to x of f of t dt. So in other words, what I'm saying is that if you integrate from 0 up to a certain x value of a function, and then take the derivative of that, you'll just get the value of the function at x. That the derivative cancels out the integral. And it doesn't have to be 0. It could actually be any value a. And so I'll make it slightly more general by making it a. So here's the proof. We're going to go back to first principles. I know that the derivative of anything can be written as the limit as h approaches 0 of the exact same function with x plus h replacing the letter x minus the function with just the letter x all over h. The nice thing is that what we're using is just the idea that the integral tells you the area under the curve. And so if you're going from a up to x plus h, let's just draw a example function here. If we're going from a up to x plus h, the first integral gives you this entire purple area, and the second integral gives you from a to x just this green area right here. So what you're really left over with is just from x to x plus h. So I can simplify my limit down to the limit as h approaches 0, 1 over h times the integral from x to x plus h of f of t dt. So the question is, what's going on with that? And the idea is that you can actually squeeze it between two different values. So the area of the underneath the curve, the area underneath the curve is always going to be between two different values. And one of those values is found by taking the lowest point, let's call that little m, and just drawing a rectangle over there. And the other value is going to be found by taking the highest point, let's call it big M. And the area is always going to be, the true area under the curve is always going to be bigger than what you would get with a rectangle at a height of little m, and smaller than what you get with a rectangle at the height of big M. So what I can say is that this area right here is in between two different values right there. Okay, and so the size of this rectangle has an h value of has an h value of has a base of h and then has an m as its height. So what I can say is that our limit is squeezed in between these two values. M times h is less than the limit as h approaches 0 of x times x plus h of f of t dt, and that's less than or equal to capital M times h. And so all I'm just saying here is that the true area underneath the curve is bigger than the shortest point, making a rectangle, but it's smaller than the tallest point, and it's making a rectangle over there. So to make it fit with our definition here, we have a 1 over h that we add in to all three of those pieces right there. And we have a limit that we add in to all three of those pieces there. So after we cancel some stuff out, what we can show is that m is less than or equal to the limit as h approaches 0 of 1 over h times x to x plus h of f of t dt, and that's less than or equal to capital M. Now here's the magic though. I should have my limit still on there, sorry. The beauty of this argument is that as h approaches 0, your function no longer obtains different values for the maximum and minimum. As h approaches 0, the maximum and minimum values of the function are the same. And in fact, we can say more than that. As h approaches 0, m is equal to m, little m is equal to big M, and they're both equal to what the value of the function is, which is f of x itself. So we're able to conclude then that this middle chunk right here is actually equal to f of x. And so we just proved that the derivative of the integral from a to x of f of t dt is equal to f of x. In other words, we just proved that the derivative cancels out the integral. A way to think about this geometrically is that as you go a little bit further to the right, the amount of area you are adding is equal to the height of the function. In other words, the rate of change of the area is the function itself. So then the other piece of the fundamental theorem of calculus goes the other way. Okay? And so what we can do is write that, let me clear the screen here. The other claim for the fundamental theorem of calculus is that the integral from a to b of a derivative is equal to f of b minus f of a. Okay? So what we are going to assume here is that we're going to assume that there exists some function whose derivative is equal to f's derivative. And if that's true, if two functions have the same derivative, then what we know is that one function is equal to the other function plus a constant. Okay? In other words, what we know is that they can only be a constant different from each other because they always have the same slope at every point. So the only difference can be that one is slid up or down from the other one. Okay? So what we can do then is look at a to b of f prime of x dx. This is going to be the area underneath the curve from A to B, and it's going to equal, one second. Yes, I got a little bit ahead of myself here. Let's go backwards just a few seconds here. What we're going to do is use what we just proved. We're going to define a function before we assume anything about it. So I got a little bit ahead of myself. Let's define g of x to be the integral from a to x of f of t dt, f prime of t dt. What we just proved is that if I take the derivative of an integral, that they cancel out, right? So I just proved in the first 10 minutes of this video that I can cancel these pieces out and get that g prime of x equals f prime of x. And then this is the part where I was getting a little ahead of myself, that g of x is equal to f of x plus c. In other words, the two functions are the same, they only differ by a constant. So it's g of x minus f of x equals c. Now by definition, g of a, here's our definition, right? By definition, g of a is the integral from a to a of f prime of t dt. Well, how much area is under a rectangle that has 0 width? It's got to be 0. But we also know that g of x equals f of x plus c, or in other words, g of x minus f of x is c. So now we know that g of a minus f of a is equal to c. And we also know that g of a is replaceable with 0. So I promise this is going somewhere. We know that 0 minus f of a is equal to c. So we know that f of a is equal to negative c. So then what I know is that if I go back to my function right here again, I know that g of b minus f of b, just a second. All right, sorry about the interruption again. So where were we at? We were talking about what g of b is. So g of b minus f of b has to equal c. And we just figured out that c over here is negative f of a. So guess what we've got now? G of b minus f of b is negative f of a. So g of b equals f of b minus f of a. And that is it. What that means is that if we go back up to our definition of g right here, we just proved that g of b is equal to f of b minus f of a, and that's the same as doing the integral from a to b of f prime of t dt. So we know that this value right here has to equal f of b minus f of a. So we proved that when you have the derivative on the outside of an integral, you can cancel them out. And then in the second part, we proved that if you have the integral on the outside of a derivative, you can cancel them out. So sorry about the couple interruptions in the video and the misstep I took on this second part, but we got through it. Please comment and let me know if there's anything I can do to help out. Thank you.